Picture a car on a highway. Pressing the accelerator changes the engine speed, and the engine speed changes how fast the car covers distance. Speed up the engine a little, and the whole chain reacts. The wheels turn faster, and the distance changes faster too because the rates multiply through the chain. That is the whole idea behind the chain rule. Suppose y is a function of u, so y equals f of u, and u is itself a function of x, so u equals g of x. We want to know how y changes with x, and the trick will be to relate it to how y changes with u, and how u changes with x. By first principles, the derivative, dy by dx, is the limit, as change in x goes to 0, of open bracket change in y, divided by change in x, close bracket. Right now, change in y depends on x only through the middle variable u, so we need a way to bring change in u into the picture. Here's the key move. We multiply and divide by the same non-zero quantity, change in u, without changing the value of the expression. This turns our ratio into open bracket change in y divided by change in u, close bracket times open bracket change in u divided by change in x, close bracket. Now take the limit as change in x goes to 0. Since u depends on x, this also forces change in u to go to 0, provided u is well behaved, so the first ratio becomes the limit, as change in u goes to 0, of change in y divided by change in u, which is exactly dy by du. The second ratio becomes the limit, as change in x goes to 0, of change in u divided by change in x, which is du by dx. Formally, the two change in u terms cancel, just like fractions, even though we must be careful because this is really a limit argument, not literal division. Putting the two pieces back together gives the chain rule. Derivative of f of g of x equals f prime of g of x times g prime of x. In words, the rate of change of y with respect to x equals the rate of change of y with respect to u, times the rate of change of u with respect to x, exactly like the car's speed and distance rates multiplying through the chain. Before we compute anything, let's predict. Take y equals the quantity x squared plus 1 cubed. Using the rate multiplication idea, if we let u equal x squared plus 1, then y equals u cubed, so dy by du should be 3u squared, and du by dx should be 2x. The chain rule predicts the final derivative should look like 3 times the quantity x squared plus 1 squared times 2x. Let's check this by direct expansion. First, the direct method, we expand the quantity x squared plus 1 cubed term by term. This gives x to the 6th plus 3x to the 4th plus 3x squared plus 1. Now differentiate this expanded polynomial term by term. The derivative of x to the 6th is 6x to the 5th. The derivative of 3x to the 4th is 12x cubed. The derivative of 3x squared is 6x. The derivative of the constant 1 is 0. So the direct derivative equals 6x to the 5th plus 12x cubed plus 6x. Now let's redo it with the chain rule using our predicted setup. Let u equal x squared plus 1, so y equals u cubed. Then dy by du equals 3u squared, and du by dx equals 2x. By the chain rule, dy by dx equals dy by du times du by dx, which equals 3u squared times 2x. Substituting back u equals x squared plus 1, this becomes 3 times the quantity x squared plus 1 squared times 2x, which simplifies to 6x times the quantity x squared plus 1 squared. Let's expand this chain rule result to compare with the direct answer. The quantity x squared plus 1 squared equals x to the 4th plus 2x squared plus 1. Multiplying by 6x gives 6x to the 5th plus 12x cubed plus 6x. And that matches exactly what we got from direct expansion, 6x to the 5th plus 12x cubed plus 6x. Same answer, two completely different roots, which is exactly why the chain rule is trustworthy as a shortcut. It just saves us from expanding messy powers by hand. That wraps up this derivation. If this helped build your intuition for the chain rule, Please like and subscribe, it really helps the channel. This also completes our current batch of derivative videos, so next time we move into a brand new batch, starting with integration and beyond.